Welcome to my class. I'm Drew Collop. In today's class, we're going to continue on talking about dilutions. Specifically today, we're going to talk about serial dilutions. Let's talk about the term serial. This might sound kind of strange, but what's the difference between a killer and a serial killer? Well, a killer kills once and then doesn't kill again. A serial killer kills once, kills again, and again, and again. This is a strange example. Sometimes these strange examples will help you to understand concepts in the lab. A dilution, we dilute once and we are done. With a serial dilution, we dilute, we mix, we dilute again, we mix, we dilute again, we mix, so on and so forth. Very important step in between is the mixture phase. I'll explain that throughout this lecture. So at the end of last lecture, I spoke about doing a 1 in 1 million dilution. Sometimes we have to make very large dilutions, a large dilution factor. As a result, we do several sequential dilutions in a row. We try to be as accurate as possible from start to finish. Any issues with measuring of our volume from one step to another will have huge changes in the end of a serial dilution. Also, make sure you mix completely prior to doing your next dilution. If your solution is not mixed, again, you will not have a proper final solution. Let's examine how you would prepare a 1 in 1 million dilution. So we start with our stock solution. This is going to be our initial stock, and we want to dilute that 1 in 100. What I can do is I can take 1 ml of my stock solution, place that into 99 ml of solvent. This will give me a total of 100 ml. As a result, I will have 1 part stock and 100 parts total solution. So here, this would be very concentrated. And here, this would be less concentrated, more dilute. We would thoroughly mix this and then do it again. Take 1 ml of that new solution that's fully mixed, place it in 99 ml of solvent, giving me 100 ml total solution. 1 part solute over 100 parts total solution. Again, we'd mix that up. And this would be even more diluted. One more time. Take 1 ml of that new solution that's been fully mixed and place that into 99 ml of solvent. 100 ml total, 1 part solute over 100 parts total solution. The solution will be very diluted. So this is how we would perform a 1 in 1 million dilution. We don't require 999,999 ml of solvent. We require about 300 ml. To accurately perform a serial dilution, your liquid handling techniques must be excellent. Please make sure in your first year you take that skill very seriously. If you can't accurately measure 1 ml or 99 ml, there's not a chance you will be accurate with this dilution. How do we know this is 1 in 1 million dilution? Well, what we do is we look at each of these values here. We take each one as a fraction and we multiply them together. So I had 1, 2, and 3 1 in 100 dilutions. 1 times 1 times 1 is 1. And we have 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6 zeros. 1 in 1 million dilution. So this would be referred to as your total dilution. So when doing a serial dilution, we can take each of the individual dilutions and multiply them together to get the total dilution. Once again, understanding how to work with fractions, very important in the lab. To determine the new concentration of a diluted sample, we can use this formula here. So the new concentration is our stock concentration multiplied by our total dilution. So as an example, if I took my stock solution, I did a 1 in 1 million dilution, I would take the stock, divide by 1 million, and this would give me my new concentration. I would now like to introduce the concept of your dilution ratio. This is a ratio between the initial solution and your final solution. V1 compared to VF. Notice we can build this formula by rearranging our dilution formula. We want to know the new concentration. We have the initial concentration. Here I have to multiply by my total dilution. This total dilution is referred to as my dilution ratio. And you can see I just rearranged the equation. CF on one side, C1 times V1 over VF, but I keep these together as a fraction. This is my dilution ratio. As an example, V1 would be 1, VF would be 1 million in a 1 in 1 million dilution. So as you can see, this right here comes from our dilution formula. The total dilution is our dilution ratio. It is our initial volume divided by our final volume. Let's now examine example 1. If a stock solution is 75% weight by volume sodium chloride, it is diluted 1 in 20, and then this new solution is diluted 1 in 30. What is the concentration of the final solution? C1 V1 equals CF VF. My stock solution, concentration, 75%. What I want to know is what the new concentration is going to be. Let's rearrange it. Now I need to figure out my total dilution for the serial dilution. So initially, I did a 1 in 20 dilution, and then I did a 1 in 30. Multiply those together, 1 over 600. Let's rearrange that so we have the dilution ratio. This here is your dilution ratio, the total dilution. Now we can solve this. CF equals my initial concentration, which was 75.0% weight by volume. I then multiply by my dilution ratio, 1 over 600. This will give me 0.125% weight by volume. So as you can see, we calculate the total dilution by multiplying all the individual dilutions in our serial dilution. This will then give me my dilution ratio, and I can use this to calculate what my final concentration will be. Let's look at another example. This is something you might actually do in a biology lab. We have a bacterial culture. Bacteria are very small. They grow very rapidly, exponentially. Sometimes we need to figure out the concentration of these cells. The stock solution can be too concentrated to count directly. Consequently, we perform a serial dilution, we count those cells, and then we can calculate what the initial concentration was. Let's examine this. We have a bacterial culture. We know actually what the concentration is of the stock solution. We need to do a serial dilution to dilute it down. Perhaps we need to plate this, grow the bacteria on plates. We perform a 1 in 1,000 dilution, and then a 1 in 100 dilution, and finally a 1 in 20 dilution. What is my concentration in my final dilution? So what's my CF? Now along the way, you'll have many tubes when you do this. We don't care about the concentrations in between. As long as we've done them correctly, that's fine. We will be using, though, the final tube that is diluted. So what's the concentration in this tube? C1 V1 equals CF VF. I know my initial concentration. I want to know what my final concentration is going to be. Let's rearrange that. Let's rearrange it so that the volumes are separate. Let's now calculate the total dilution. I start with a 1 in 1,000 dilution. I then perform a 1 in 100 dilution. I then perform a 1 in 20 dilution. This will be a 1 in 2 million dilution. This is my dilution ratio. I can use that here. Let's sub in and solve. So my initial concentration, multiply by my dilution ratio, and this will give me my final concentration. 5 times 10 to the 9 divided by 2 million, 2,500 cells per mil. This means if I took 1 milliliter of my final dilution in the serial dilution and I place that onto a plate, that means later on I should have 2,500 colonies of bacteria growing on my plate. Notice there was one more question here. How many cells are in 5 mils of the total solution? This is a concentration. This states that 2,500 cells is equal to 1 mil. We can use this as a conversion factor. Let's do that now. So I want to know how many cells are in 5 mils. To do that, we're going to convert from milliliters to cells. I will then use this as my conversion factor. My concentration was 2,500 cells per mil. You can see mils cancel out. 5 times 2,500, 12,500 cells. This is an important calculation in the laboratory. If we need to seed a culture for the next day, I would take 5 mils of my diluted solution to obtain 12,500 cells. Now we've talked about a dilution ratio. Let's talk about a dilution factor now. I spoke about this earlier. Oftentimes you need to do a large dilution because your stock solution is far too concentrated. We have many instruments in the lab that can quickly and accurately count cells. However, that solution has to be diluted. What we would do, we would dilute the cells down to get a diluted concentration. We would then multiply by my dilution factor, and this would tell me what my stock solution was. The dilution ratio was comparing the initial volume to the final volume. My dilution factor is the reciprocal of that. I'm comparing your final volume to your initial volume, right here. Again, we can use our C1V1 equals CFVF to rearrange. And here we get our dilution factor. So notice it is just the reciprocal of my dilution ratio. If my dilution ratio is 1 in 1 million, then my dilution factor is 1 million over 1. Again, your dilution factor is the reciprocal of your dilution ratio. The reason why we want to use a dilution factor is to calculate what the initial stock concentration is if we dilute down our solution and count it there. In a cell biology lab, you're going to be doing this all the time. Let's examine this problem here. So again, we have a bacterial culture. It's very concentrated. Too concentrated for our machines to accurately count. So we'll perform a dilution, not just any dilution, a serial dilution. We will count the diluted solution, and if we know our steps to create that serial dilution, we can calculate what the initial stock concentration was. So here we took a bacterial culture. We started by diluting it 1 in 100. We took 2 mils of that and added 8 mils of media. 1 mil of this dilution was plated and it produced colonies. The question is what is your initial concentration of your stock solution? So let's look at dilution ratio and dilution factors. So my dilution ratio, starting with a 1 in 100 dilution. I then go to my next dilution. I'm taking 2 mils of solution and I'm adding 8 mils of media. So be careful, this is a tricky one here. Remember the volume on the bottom is the total solution. So I have to add the 2 to the 8. We will then calculate my dilution ratio, 1 over 100, 2 mils over 10 mils. Notice my mils cancel out here. I have 2 over 1,000. This would be my dilution ratio. However, let's simplify it down. 1 over 500 is my dilution ratio. Again, being able to work with fractions efficiently is very important for your lab work. Now we have the dilution ratio. The dilution factor is the reciprocal. As a result, we flip it, and we have 500 over 1. It says we took 1 ml of that solution and we plated it, meaning we put it on a plate with growth media, and we obtained 20 colonies. So here's our plate, an agar plate perhaps, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Might look something like that. So initially, bacteria is too small to be seen with the naked eye. What we can do is we can plate these cells, place it in the proper environment for growth, and they will grow exponentially. One cell will become 2, and then 4, 8, 16, 32, 64, 128, 256, 512, 1028, so on and so forth. In a short period of time, that individual cell will replicate and produce more cells. It would create a small circle of cells. We call this a colony of cells. Again, it will originate from a single cell if you've distributed your cells properly on your dish. From this, we determined that this has a concentration of 20 cells per 1 ml, right? We added 1 ml, we got 20 colonies, meaning initially there would have been 20 cells plated. The question now is, what was the initial concentration of your solution? C1V1 equals CFVF. So I know my final concentration, 20 cells per 1 ml. Well, I want to figure out what my initial stock concentration was. Let's rearrange it. Let's rearrange it so that we have our dilution factor here. Again, we have our final volume over our initial volume. The final concentration, 20 cells per ml, multiplied by my dilution factor. My dilution factor is right here, 500 over 1. 500 parts final for every 1 part initial. Work that out. We have 10,000 cells per ml. So to summarize, we can use our dilution factor to calculate the initial stock concentration, or we can use our dilution ratio to calculate a final concentration. Dilution factor is the reciprocal of the dilution ratio. I'd like you now to pause your video and try this one on your own. We have a highly concentrated culture of bacteria. It was serial diluted 1 in 100 times, 3 times. So we did a 1 in 100, we mixed. We did another 1 in 100, we mixed. And we did another 1 in 100. We mixed that. This will be our final dilution. We counted the solution and we determined the concentration of cells to be 3.2 times 10 to the 2 cells per ml. The question is, what's the concentration of your original stock solution and how many cells will be in 10 ml of your stock solution? So pause your video, try that now. Let's take it up. Let's calculate the dilution ratio first. Dilution ratio, I'm taking all my individual dilutions and I'm multiplying them together. This will give me 1 in 1 million again. Our dilution factor will be the reciprocal of your dilution ratio. This will be 1 million over 1. They are reciprocals. I want to determine what the concentration of my initial stock was. C1V1 equals CFVF. I want to know my initial concentration. We'll rearrange. Keeping my volumes together as a fraction. This will be my dilution. My final concentration I have right here. I will sub those in and solve. When you write your dilution factor, please don't write 1 million. Please write 1 million over 1 so that I understand that you know where this comes from. Solve it now. Initial concentration will be 3.2 times 10 to the 2. 1 million is times 10 to the 6. So 3.2, 2 plus 6 is 8. No calculator required. So from this calculation, we determined that the initial stock concentration before the serial dilution was 3.2 times 10 to the 8 cells per mil. There was one more part to this. It asked how many cells would be in 10 mils of my stock solution. Again, I can use this as a conversion factor. This says 1 mil is equal to 3.2 times 10 to the 8 cells. Anytime two things are equal, they can be a conversion factor. I want to convert from 10 mils of my stock to cells. 1 mil goes on the bottom, so they cancel out. 3.2 times 10 to the 8 goes on the top. Mils cancel mils. No calculator required. 3.2 times 10 to the 9 cells. You don't quite understand how important this calculation is yet, but in cell biology, plating cells accurately is extremely important. If you can't do that, you can't work in cell biology. Let that be bacterial cells or mammalian cells. I'm now going to review how to accurately set up a serial dilution. I've talked about some serial dilutions today, 1 in 100, then 1 in 100, 1 in 100. But how do you determine how to accurately and properly set up a serial dilution? That will be the last topic for today's lecture. So you're in a cell culture lab. You're requested to prepare 5 mils of a 2 times 10 to the 5 cell per mil solution. You count your stock solution and you obtain 7.78 times 10 to the 8 cells per mil. Let's pretend that we didn't listen to this lecture at all and we just did a single dilution. We just used C1V1 equals CFVF. Let's see what we get. So here is my initial concentration. Here is my final concentration. And this value here is my final volume. So I need to determine what my initial volume will be. V1 is equal to, let's rearrange it. Sub in our values now. Perhaps if I color code it, it will help you. Notice, cells per mil cancel out on top and the bottom, and left with milliliters. We do the math now. That's a very small volume. Let's convert that over to microliters. Moving that over 3 decimal places equals 1.287001. Significant digits, let's just say we're going to round that off to 2 significant digits. We'll say this value here was 5.0. So we'll round this off to 1.3 microliters. So what are we going to do with this? How are we going to calculate this? Therefore, based on these calculations, it says we will mix 1.3 microliters in 4.9987 mils of my solvent. Based on our theoretical calculations, there's nothing wrong with this. However, there's not a chance you'll be accurate with this dilution. how are you going to measure accurately 1.3 microliters? A bigger question, how are you going to accurately measure 4.9987 milliliters? Not possible. In addition, oftentimes, micropipetters can be slightly out of calibration. What if your micropipetter is off by plus or minus 1 microliter? Again, you can see the problems with doing a single dilution. Consequently, we would never do a single dilution for this. That is the difference between theoretically calculating something and actually doing it. Once again, there's nothing wrong with this calculation. It works out. But in practice, this will never work out. Let me show you how I would prepare this serial dilution. Exact same values here. Again, we're starting with 7.77 times 10 to the 8 cells per mil. I want my final concentration to be 2.0 times 10 to the 5 cells per mil. And I would like the final volume to be 5 mils. Now what I will do is I would write down my initial stock concentration. I would then perform a 1 in 10 dilution. By doing that, 7.77 times 10 to the 7 cells per mil. So I could do this by taking 1 mil of cells and adding to that 9 mils of my solvent. I'm now getting closer to that value of 2 times 10 to the 5. What I will then do is I'll keep repeating 1 in 10 dilutions. Again, I could do 1 mil of cells plus 9 mils of solvent. You never want to do too big a dilution. 1 in 10 in my mind is as big as you should go. When you start going to 1 in 100, 1 in 1,000, again, you're going to get accuracy issues. In addition, taking 1 mil is better than taking 1 microliter. If you're off by a little bit here and there and you're dealing with larger volumes, there won't be such a big effect on the final concentration. Let's do another 1 in 10 dilution. Now that I've got sufficiently close to 2 times 10 to the 5, notice here, my exponent is a 5. And that's where I want to get. Now I'm going to use my C1V1 equals CFVF for my final dilution. I'll rearrange it. V1 is equal to CFVF over C1. Sub in my values now. I'm using this right here. 2.0 times 10 to the 5 cells per mil times 5 mils divided by 7.77 times 10 to the 5 cells per mil. These will cancel out. 10 to the 5 and 10 to the 5, they also cancel out. 2 times 5, which is 10, divided by 7.77. 1.287001287 milliliters. As a result, I will take 1.3 mils of my cells and add to that, my total concentration will be 5 mils. So I will add to that 3.7 mils of my solvent. A lot of steps along the way. I will have my stock solution. I will have 1, 2, 3, 4 dilutions. So that's the math behind it. Let me show you what it looks like. So here's my stock. I'm going to take 1 mil from this. I'm going to add it to 9 mils of total solution. That'll be 10 mils. This is a 1 in 10 dilution. I will then thoroughly mix that. I will take 1 mil of that to 9 mils of solvent, and that'll give me 10 mils total solution, another 1 in 10. Mix that, take another 1 mil, add that to 9 mils of solvent, 10 mils total, another 1 in 10. So we've done 1, 2, 3, and we will do 4 right here. So here we're going to take 1.3 mils of solution and add that to 3.7 mils to give me a total of 5 mils solution. I will mix this thoroughly, and if I've done this correctly, this will be 5 mils of a 2.0 times 10 to the 5 cells per mil solution. Now I give you this question. What if your pipetting device is plus or minus 1 microliter here? Won't be much difference at all. Let me clarify that because this is in milliliters, not microliters. Now, I've said this before. I will repeat it. I teach an upper semester course in tissue culture. This is what I teach them in their last semester. However, they will perform this dilution. They will grow their own cells up. They will harvest those cells. They will count those cells. I will give each of them a different final volume and a different final concentration I desire as a dilution. They will perform that dilution. They will then count the concentration of the final tube, and they will do a percent error calculation, comparing what they got to what I asked for. This is their final practical exam. They must be within 10% error to get full marks. Anything higher than 10% error, they begin losing marks. This is not something that just happens overnight. These students must practice this all semester. Being able to accurately serially dilute a cell culture is a key skill to have when working in the industry. If you can't do that, you won't hold down a job in cell biology very long. I'm happy to report that the vast majority of students are within 5% error, and I've had students with 0% error in the past. So this is a key skill. If you're going to go into biotechnology, you need to know this. Once again, fractions, very important. I would like to cover some serial dilution best practices. Things you should do and things you shouldn't do. Number 1, mix in between thoroughly, extremely important. Ensure your solution is homogeneous throughout. If it is not mixed thoroughly, you're not going to get an accurate serial dilution. If you want to be accurate, never do anything bigger than a 1 in 100 dilution. And it's best to have no volumes less than 10% the final volume. I would prefer 1 in 10s only. Larger volumes are better. They're easier and more accurate to measure, and don't use any volumes less than 1 mil. In my lab, I don't allow the students to use micropipettes to do these serial dilutions. They use serological pipettes. Consequently, their skills with a serological pipette, very important. Also, make sure your equipment is calibrated. If your equipment is not calibrated, there's no way you can possibly get the correct dilution. And try and be as accurate as possible in your liquid transfers on every dilution. Any mistake along the way will ruin the entire serial dilution. Also, only the final dilution is used. This will contain your final dilution volume. You can count that, and then you can use it to set up some experiments. I would now like you to try and calculate the correct dilutions for this serial dilution. Please note, you don't always have to do 1 in 10 dilutions. You can do 1 in 2s, 1 in 3s, 1 in 4s, 1 in 5s, so on and so forth. That is a hint to solve this problem. So your steps are, do dilutions until you get into the ballpark of where you want the final concentration to be. You want a final concentration of 6.5 times 10 to the 4 cells. So you want to be around times 10 to the 4. Use your dilutions to get there, and then use C1V1 equals CFVF to get that final dilution. Try that now. Okay, let's take it up. I'm starting with a 10 mil tube of 5 times 10 to the 6 cells per mil. I want to end up with a 4.5 mil tube of 6.5 times 10 to the 4 cells per mil. So I'm starting with 5.0 times 10 to the 6 cells per mil. The only purpose of this 10 mil volume here is to tell you you can't take more than 10 mils. I will perform a 1 in 10 dilution. I'm going to take 1 mil of cells and add to that 9 mils of my solvent. This would be usually media. This will give me 5.0 times 10 to the 5 cells per mil. I will then perform another 1 in 10 dilution, taking 1 ml of this new dilution of cells and add to that 9 ml of my solvent. This will then give me 5.0 times 10 to the 4 cells per mil. Looks good, right? We want to get close to times 10 to the 4, and here I have times 10 to the 4. Looks good, right? Wrong. Do you see the problem? I've overshot. I want 6.5. I overshot, I got 5.0. As a result, I should do a different dilution. Let's say a 1 in 5 dilution. This means I take 1 ml of cells and I add to that 4 ml of solvent. Divide 5.0 times 10 to the 5 by 5. I get 1.0 times 10 to the 5 cells per mil. Now, I'm relatively close. 10 versus 6.5. So now I will use C1V1 equals CFVF. I want to know what my initial volume is going to be. I will solve for that. I will sub in and solve. My final concentration, I want 6.5 times 10 to the 4 cells per mil. And I want 4.5 milliliters of that. I'm now going to be using this concentration here in my calculation. 1.0 times 10 to the 5 cells per mil. Cells per mil cancel out. 6.5 times 10 to the 4 times 4.5 divided by 1 times 10 to the 5. This will give me, let's round this off to 2 significant digits, approximately equal to 2.9. What is my units? My units are milliliters. I would like 4.5 mils of that. I will take my 4.5 mils total solution, subtract away my 2.9 mils of cells, and this will give me the milliliters of solvent I need to add. 1.6 milliliters of solvent. Therefore, mix 2.9 mils of cells with 1.6 mils of solvent. This should give you an accurate dilution. So a couple things here. Notice I have no dilution bigger than 1 in 10. Also notice I'm not taking any volumes less than 1 mil. Taking a volume less than 1 mil can be challenging using a serological pipette. Try and be as accurate as possible. With these techniques in hand and some practice, you should have no problem performing a serial dilution. We've now completed all of the concepts of dilution for our first year math class. I have a large number of practice problems here tying everything together. 1, 2, 3, 4, 5, and 6. And I even have the answers here to double check. Try these questions. I'm not going to take any of them up. If you have any difficulties with them, ask me during tutorial or outside of class. That's all for today. Until next time.